Hello everyone and welcome to this week's lecture. Today we'll be exploring one of the most fundamental concepts in both AI and risk management, which is data itself. So before we can apply any AI techniques or develop any sophisticated risk management models, we must first understand what data is, how it's structured, stored, and prepared for analysis. This foundational knowledge is crucial because it's very important to make sure the quality and understanding of our data uh, is directly related to the effectiveness of any AI system we build. Today's lecture will provide you with a comprehensive understanding of data types, storage formats, variables, and data preparation techniques, which are all essential for successful AI implementation in risk management context. Let's begin by outlining the key concepts that we'll cover in today's lecture. So we have three main focus areas. First, we'll explore understanding data and its various types. It's not just about knowing that numbers exist or that text exists, but really understanding the fundamental nature of different data types and how they impact our analysis and modeling decisions. Next, we'll examine data storage functions, specifically how data is stored and handled by the programs that run our systems. So in the world of AI and risk management, we're often dealing with massive data sets from multiple sources. So understanding how this data is organized and accessed is crucial for building efficient systems. And finally, we'll discuss data storage itself, the various formats and structures we use to organize and maintain our data, the knowledge of this data storage will help us make informed decisions about data architectures when implementing AI solutions for risk management. These three concepts form the foundations of data literacy that every AI and risk management professionals need to know. So first, what is data? At its most basic level, data is a collection of discrete values that convey information. But let's break this down further because this definition has different important components here. When we say discrete values, we mean individual, different pieces of information. So this could be numbers like customer credit scores of 750 or characters like the letter A representing a credit rating, or even complex strings like a customer's full name. These values describe quantity, like how much money was borrowed, quality, like whether a loan application was approved or rejected, facts, like the date a transaction occurred, statistics, like the average default rate in a portfolio, or other basic units of meaning that help us understand and analyze business situations. The key phrase here is may be further interpreted. Raw data by itself often doesn't tell us much. For example, the number 750 by itself is meaningless. But when we know it represents a credit score, then it becomes valuable information that can influence lending decisions. A datum, the singular form of data, is simply an individual value within our collection. Think of it as a single cell in a spreadsheet or a single field in a database record. While each datum might seem insignificant alone, when we combine many data points, we can uncover patterns, trends, and insights that drive effective risk management strategies. Now let's look at the different types of data, or as we say in computer science, data types. Understanding data types is crucial because different types of data require different storage methods, different processing techniques, and different analytical approaches. So we can break down data types into three main groups. First, we have fundamental or primitive data types. These are the building blocks of all data systems. or in other words, the basic types that programming language and database systems understand. Numbers come in several varieties. Integers, for example, for whole numbers. These are perfect for counting things, like numbers of loan applications, for example, received. Float and double are for decimal numbers like 1.5 or 3.145. In risk management, we might use float for interest rates, for probability calculations, obviously, or financial ratios. Characters occupy 1 byte of memory and represent single letters, numbers, or symbols. Examples include uppercase A, lowercase a, and so on. You might use these for simple codes or flags in your data. Strings are groups of characters that form words or phrases. For example, 1, 2, 3, 4, or Smith, or approved. These are essential for storing names, addresses, descriptions, or any textual information. Boolean values only take two values, true or false, or yes or no. These are very useful in risk management for binary decisions, like whether a loan was approved, or a customer defaulted, or whether a transaction was flagged as suspicious. The second category of data is derived data types, which combine primitive types. So the most common example is date time, which combines numbers to represent specific points in time. And finally, we have abstract or user-defined data types, which are custom structures that developers create for specific business needs. So let's look deeper on fundamental data types, since they're important for our work in AI and risk management. Fundamental data types are built-in or predefined data types that can be used directly by programmers and database designers to declare variables and structure data. Think of these as the basic vocabulary of the computer world. Integers handles whole numbers and are perfect for counting discrete items. So, for example, you could count the number of defaults in a portfolio, the number of days since last payment was made, the number of credit inquiries a customer has made. Characters, which typically require just 1 byte of memory space, might seem simple, but there is a foundation of all text-based information. So even though we live in an era of big data, understanding that each character takes up space helps us design efficient storage systems. The efficiencies of these primitive types is crucial when you're dealing with large data sets common in AI application. For example, if you're analyzing millions of transactions for fraud detections, choosing the right data type can mean the difference between a system that finishes the job in minutes versus hours. Boolean values, while simple, are very powerful in risk management because they can represent binary outcomes that are central to many risk models. Default, no default, fraud or no fraud, approve or reject. Many machine learning algorithms work exceptionally well with Boolean features because they're simple and computationally efficient. So this table right here shows you a comprehensive review of how different data types are implemented at the system level. So this can look technical, but it's important that you get an understanding when working with large-scale AI for risk management. Notice how different types require different amounts of storage space measured in bits. A character uses 8 bits, while some integers can use up to 64 bits. This matters when you're dealing with millions or billions of records. The storage requirements can add up quickly. The value ranges shown here are also crucial for data validation and system design. For example, if you're storing customer ages, you know that a standard 8-bit unsigned integer from 0 to 255 would be sufficient. But if you're storing account balances, you might need a much larger integer type. The difference between signed and unsigned numbers is very important in financial application. Signed numbers can be negative, which is essential for representing things like account overdrafts or negative returns. Unsigned numbers, on the other hand, can be positive only. So these can be used to represent larger positive values with the same storage space as the signed integer. Floating point numbers have their own complexities with different levels of precision. In risk management, precision matters enormously. So a small rounding error in an interest rate calculation when multiplied across millions of transactions can result in significant problems. So understanding these technical details helps you make the good decisions about data architectures and ensure your AI systems can handle the scale and precision requirements of real-world risk management applications.